inspired you to stick with it. So I'm currently at Emory University in Atlanta, Georgia. And I am very soon going to be at the University of Wisconsin-Madison. I'm moving my group over the course of the next few months to start there as a professor of both chemistry and astronomy. Emory doesn't have an astronomy department, so this is a really exciting opportunity for us to have astronomers next door and branch out in our research program. So I am trained as a chemist. All of my degrees are in chemistry. But my thesis project was at Caltech with Jeff Blake, and it was 50-50 lab work and astronomy, and I have ventured into astrochemical modeling since then. So I do a little bit of all of it. So when we were deciding how to divide up the lectures, I was like, which part do you want me to fill in? Mike and I had a plan. He was going to do the introduction, and I was going to do complex molecules, but I'm before him. So I've been sitting over here adding in slides. So I wanted today give you kind of the basics of how chemistry works in the interstellar medium and how the physics influences the chemistry. John did a great job of setting up the physical conditions and the kind of strange way we think about chemistry in space compared to what chemistry is terrestrially. So I want to show you some of the basics of the processes that happen in terms of chemistry in interstellar regions, and then start to set up where we go from there in terms of the molecules we can see, how we see them, how we get laboratory spectra, and so on. So, I don't know, we'll see. There are about 3 of us that could teach any aspect of molecular spectroscopy, reactions, and radio astronomy, so we'll see how we divide this up over the course of the next few days. I don't know that many of us have posted our slides yet, because we're talking to each other and trying to figure out how to divide up the topics. So John did a great job getting us introduced to kind of the interstellar medium and what the physical conditions are. So I always like to start with this to get everybody on the same page. So this is the Eagle Nebula, the very famous Hubble Space Telescope picture. For comparison to the interstellar medium, the stuff between the stars, Earth at sea level has about 10 to the 19th molecules per cubic centimeter in the air, temperature, room temperature 300 Kelvin, and we are 10 to the 11th meters from the sun. That's that astronomical unit we were hearing about earlier, not to be confused, chemists, with the atomic unit. My husband is an inorganic chemist, and the first time he saw the size of a neutron star in AU, he was very confused. If you take one arm of the Eagle Nebula, this entire interstellar cloud, it's 10 to the 16th meters across. So this is 5 orders of magnitude bigger than the distance between Earth and the sun. If you look at the diffuse interstellar medium, so not in the dark clouds that we can't see through with optical light, but the diffuse interstellar medium, 1 to 10 molecules per cubic centimeter, 99% of the universe is hydrogen, so most of it's atomic and molecular hydrogen, and about 50 Kelvin. This is warmer than you would think. There's a lot of ionizing radiation in the diffuse medium. When you go in dense interstellar clouds, cold dark clouds, where that radiation is shielded because the light, the UV light can't get through the cloud, the density goes up to about 1,000 molecules per cubic centimeter, but the temperature goes down to 10 Kelvin. So you're working at a very low density compared to anything we can do terrestrially, but also an incredibly low temperature in these dense interstellar clouds. And this is why people didn't think molecules existed in space. It's very hard to get chemistry to go under these conditions. In hot cores, which are star-forming regions, the star is still embedded in that gas and dust of the dense cloud, but the star has started to turn on and heat things up. So in hot cores, the density goes up because gravitational collapse has happened. Even in that star-forming region, the gas around the star is still only 10 to the 7th molecules per cubic centimeter, but the temperature has now gone up to about room temperature. It's at least a few hundred Kelvin in most of these sources. And so what we see when we look at the chemistry as stars evolve is that we see very unsaturated, unstable, weird species in the diffuse interstellar medium. Dense interstellar clouds get more terrestrial-like, but the chemistry is very limited by the temperature and the density in that region. And then in hot cores, where we have a constant exchange between the solid and the gas phase, the temperature is much warmer and the density gets higher. We start to approach the sorts of chemistry that we see in a terrestrial lab. Even in those regions, we see unstable, energetically unfavored isomers. We see tons of ions and radicals. As John said, kinetics drives the chemistry of space. So today I want to walk you through how these different physical limitations guide what type of chemistry happens in these different regions and what we actually know about the reactions and the sorts of chemistry that happen and what that tells us about the physics of space. Katerina is here. She is my third-year student, and I shamelessly stole her beautiful dust grain ice picture out of her second-year report last year. Katerina makes fantastically beautiful talk slides, so thanks, Kat. So this is an interstellar cloud. If you take a look at ice and dust and gas in an interstellar cloud, you have these little dust particles. They're about a micron in size. They're much like dust on Earth. I'll talk about the composition in a minute, but it's mostly silicates and carbonaceous compounds. We can tell how big they are by taking spectra and looking at size distributions. We can look at the ices that condense out on these and dense clouds. Those clouds are at 10 Kelvin. If a molecule hits one of these dust particles, it freezes and sticks to the surface. And so we build up a few monolayers of mostly water ice with a few other species embedded in it. And then molecules are forming in the gas phase, hitting the ice and freezing, or getting ejected from the ice through energetic processing or thermal processing. Molecules in certain temperature ranges can move around on the ice and react and form new molecules. There's photon flux, there's thermal energy, there's cosmic rays, high energy particles. So there's a whole range of chemical processes that can happen, both on the dust grains and in the gas phase, and there's an interplay between the two. So I'm going to start with dust and go from there. This is a picture of a real interstellar dust particle. Earth gets hit with these all the time. There's a whole program at NASA to fly planes in the upper atmosphere and collect them. They look like dirt on Earth. So this is an SEM image of an interstellar dust particle. It's mostly silicon carbide, amorphous carbon, graphite sometimes, or aluminum oxide, or some sort of other mineral type species. A lot depends on how they form, and basically we get the dust in the interstellar medium from the death of stars. As stars start to die, they eject a lot of material into the interstellar medium, and we end up with these heavier elements that allow us to end up with dust as carbon star outflow. Interesting side note, the discovery of C60, Buckminster fullerene, was actually in an experiment designed to figure out what came out of stellar death outflows, and they by accident made C60. No one expected that result, and they kept getting this peak at C60, and it's interesting, and this is a lesson, don't pick 3 thesis advisors, because Jim Heath's actually the one that figured out the structure, but the 3 professors won the Nobel Prize. Jim did fine. Yeah, that was actually intended to simulate formation of particles like this. So if we look at these dust grains and we look at all of these different processes, I'm going to walk you through the basic chemical concepts of what happens so that we can set the framework for all the other topics that we want to discuss this week. So first up is absorption. So as I said, in these dense interstellar clouds, it's about 10 Kelvin. Anything that is in the gas phase that hits an interstellar grain can absorb and go into the ice. The only thing that really readily evaporates from grains without help at this temperature extreme is a hydrogen atom. And so interstellar dust particles are cold, everything sticks onto it when they hit, and so the rate of that adsorption onto the surface is dictated entirely by kinetic molecular theory and collision rate of molecules and atoms with the dust grains, which is dictated by the densities in the region. So we had mentioned earlier about collisions and about mean free path length. And so I'm going to back up and remind you, somewhere in the back of your brain, you did this in physics or physical chemistry sometime in your life. So you approximate molecules as a hard sphere, and the distance between, well, the radius of each of the spheres is r. So if you have two identical hard spheres, if they're just touching, the distance between the center of those two atoms or molecules is 2r. So we define the cross-section for collisions as sigma, which is pi r squared. Every molecule sweeps out a cylinder of radius 2r, within which it doesn't collide with anything else. If something's closer than 2r, they collide. The collision frequency for one moving molecule is given by this expression. But we have a real gas, which means all the molecules move. We can't just freeze everything else and move one molecule. So you statistically factor things out and you get the square root of 2 times the density times the cross-section times the velocity, if the two molecules have the same mass. So we can go through then and start to calculate collision timescales and mean free path. So mean free path, remember, is how far can that molecule or atom fly before it hits something? In a laboratory experiment, if we don't want reactions to occur in our gas, we try to make the mean free path longer than the size of the vacuum chamber. In space, we don't have walls on our vacuum chamber, so it's a matter of how far can the molecule move before it actually runs into another molecule. So we can do some pretty simple calculations here, and we can calculate that in an interstellar cloud, 99% gas, 1% dust. Let's just pick a density, 10 to the 5th seemed like a good number. Assume 10 Kelvin. Assume everything that hits a dust grain sticks, which is a big assumption, but it's a decent assumption at 10 Kelvin. The size is about, if we assume a 2 angstrom bond length, we can end up with a size of 2 times 10 to the minus 8 centimeters. We've got a cross-section based on that. Typical speeds in an interstellar cloud are about 100 centimeters per second. So you have a collision rate of 10 to the minus 8 per second, which is, compared to terrestrial chemistry, really low. This means it's 159 weeks between particles hitting in a cloud of this density at 10 Kelvin. The distance between collisions is, what is that, 10 million kilometers? So a particle in an interstellar cloud goes a very long distance for a very long time before it ever interacts with another particle. This is why interstellar chemistry is kinetically controlled, because we can't rely on the thermodynamic prediction if the two particles never meet. They can't react. So we end up with really exotic, unusual chemistry because of this. The assumption is that the two particles actually hit, something happens, for the most part. So, takeaway points. We have to assume everything sticks. There are laboratory experiments that show that that's mostly true. And the interstellar chemistry is slow if it's dominated by these collisions. So this is why people assumed that there weren't molecules in space for a long time, because they knew everything was hydrogen based on atomic observations, and they just assumed if it's all hydrogen and the timescales are so long, nothing would ever form. But we know, because we're astrochemists, that that's not true. So, if we look at interstellar dust and we do infrared absorption measurements using telescopes, we can actually get a spectrum that looks a lot like what you would take in an organic chemistry lab as an undergraduate chemistry major. So you can actually use a background star that's emitting infrared light, and you can point your infrared telescope at it, and you can get an absorption spectrum. And you can go through, here's the water. We assume most of it's water. That's the OH stretch that you see in a typical IR. You've got some methanol, some CO2. More water bands, CO. There's a nice silicate feature that's almost everywhere because that's in our interstellar dust. CO2 again. This is the older version of this spectrum. It's been repeated with more modern telescopes, but this is the one that everybody uses for their conference talks. This group would be rich if they charged for use of this picture. So we know from infrared absorption spectroscopy exactly what is happening in these interstellar ices. And we can actually get the thickness of the ice from those observations as well. Karin Oberg, Odlin Bogert, and a bunch of other collaborators actually used the Spitzer Space Telescope to go through a series of star-forming cores and a bunch of background gas observations where there were infrared sources in the back, and they could measure low-mass stars, high-mass stars, and background, and measure the components of the interstellar ices and figure out what the major chemical components of those ices were. Most of it's water. We assume water is 100% and scale everything else compared to that. There's a little bit of CO and CO2. There's tiny amounts of methanol, and then everything tapers off after methanol. So, everything we see in interstellar chemistry comes from these ices evaporating. So this is your starting material. And if you want to build an interstellar chemical model, you assume that this is what you have, and you have to go from there. And so today I'm going to walk you through some of the processes that build these molecules and then what happens to them once they start reacting. Stop me if you have any questions. Good so far? The other thing to think about, now I just said we assume water is 100% and everything else is trace compared to water. If you take water and you freeze it onto a substrate at really low temperatures and densities, you do not get crystalline water, you get amorphous solid water. So most of interstellar ice is actually amorphous solid water, which means it doesn't have a regular crystal pattern. Crystalline ice can form under some conditions, but for the most part, interstellar ice is amorphous solid water, which really impacts the chemistry because of the structure. There's lots of porous behavior within this amorphous solid water, so there are pockets where reactions can occur. The surface isn't smooth. There are binding spots. Things have to move around on the ice, and it's much easier to diffuse if it's a crystalline structure than it is if it's amorphous. So Rob Garrett at UVA actually simulated this computationally, so you can see this is what you get at 10 Kelvin, 40 Kelvin, 60 Kelvin, and 130 Kelvin when you're depositing ice on a surface of that temperature, water ice. Astrochemists will refer to anything that's solid as an ice, which confuses my chemistry colleagues. Most chemists just refer to water as ice, and everything else is solid methanol. I call it methanol ice. But this is for water ice, so you can see.
It's consistent.
What's that?
It's consistent. Lithium is metal.
Yeah. Yeah.
Everything else is just
Great. So, 10 Kelvin, you get very porous, very amorphous water ice. So all the chemistry in the solid phase in the interstellar medium happens in or on that amorphous solid water surface. We have a lot of groups in astrochemistry around the world who study ice chemistry. Most of them do infrared measurements of the ice, and then they warm it up and use mass spec to detect it. And then there are lots of experiments where they're looking at things diffusing to get diffusion barriers, get desorption barriers, which is related to the binding energy on the ice. So we have a lot of information about the very simple molecules that we know are present in these ices. What we don't know yet, and my group is actually working on, is how there's an interplay between this surface chemistry and what comes off in the gas phase, and how to characterize that. It's the gas phase chemistry that we can see with a ground-based telescope. And so that's the part that astronomers use to identify molecules in space, but it's very closely linked to what's happening on this ice surface. So I remade this schematic based on Eric Herf's very prolific background talk on interstellar chemistry to show all the different processes that can occur. You can assume every site on that amorphous solid water surface where something binds as a little potential well. Molecules can accrete and desorb on and off the surface depending on the temperature and the energetic processing. Molecules and atoms can hop over these barriers. They can tunnel through the barriers. Things can come in and react out of the gas phase directly, or two things on the surface can move and find each other and react. Or if you get something at really high energy, it can actually overcome the barrier, and that's a hot atom mechanism for diffusion on the ice surface. All of these different processes happen on an interstellar ice grain, and depending on the physics of the source you're looking at, different ones will be of different levels of importance, and depending on the molecule or the atom that you're studying. Hydrogen likes to tunnel. It's little. So we'll start with the very simple surface processes. You can have thermal diffusion. If you warm the ice up warm enough, atoms and molecules can move around on the surface, find each other at different binding sites and react. Hydrogen can always move. Atomic hydrogen. Molecular hydrogen tends to also move fairly freely. We assume the other atoms can also move at some level. The most abundant are carbon, oxygen, and nitrogen. So they tend to move around and find each other and undergo single atom addition reactions. You can have tunneling if you have the right conditions. So hydrogen also tunnels through these barriers rather than just diffusing. And there are different energies associated with those different processes. Once you get up to molecules, so the simplest molecules are things like CO and CO2, and then the heavier molecules, methanol, formaldehyde, ammonia, those have really big binding energies with the water ice. And so they don't diffuse unless the star starts to warm up. At 10 Kelvin, nothing moves except hydrogen. At 20 Kelvin, everything moves. And so we can actually model this in the lab. We can take spectroscopic measurements and we can calculate binding energies with the surface of a water ice for each of these species, and then put that into models to try to understand the sort of chemistry that happens. There is exchange between the gas and the surface, and there's two major mechanisms for that. The first is the most predominant. This is the Langmuir-Hinchelwood mechanism, where you have particle A and particle B in the gas phase. They both hit the ice and stick. They both diffuse on the ice. Eventually they find each other and they form a new molecule, and it either stays on the surface or under some conditions it forms with enough internal energy it can get kicked off the ice back into the gas phase. So we think this is the major formation mechanism for most molecules that we see in the ice, and also the molecules we see in the gas in dense clouds. The other thing that can happen is the Elie-Rodal mechanism, where here instead of two low energy particles sticking and finding each other, you have one on the surface and one that comes in at high energy and hits it directly. They react and you form a new molecule. So this can happen, but statistically is much less likely than the two things stick and scour the surface and find each other. But both mechanisms actually can happen. There used to be a debate, a raging debate about molecular hydrogen formation based on these two mechanisms. I've been around long enough that debate's calmed down. When I was a grad student, that was like half of every astrochemistry meeting was arguing about these two mechanisms. Not anymore. We know that we can process ices. So you have direct photons from a star or another type of source. You can have thermal energy. If it's close enough to the newly formed star in a hot core, you can heat the ice up. And you can also have energetic particles called cosmic rays. So all of these can process this ice and drive more complex chemistry. And so that's how I'm going to spend the rest of my talk, is talking about what happens in the ice and then what happens when they evaporate. So again, if we have amorphous solid water, we can have compact amorphous solid water, or we can have porous amorphous solid water. If it's porous, all sorts of things can get trapped in these pores. Some people like to call these nanobeakers. You have species trapped in here, and they can photonize, or they can get dissociated with cosmic rays. The parts can react because they're trapped in a pore, and then form new molecules. So the surface chemistry is dictated by what type of ice you have and what the binding energies are and how smooth it is as to what the diffusion barriers are. So there are groups that study ices that basically lay down water ice and all of these different types of arrangements and then look at how that changes the chemistry. Cosmic rays are the most predominant processing mechanism in dense clouds and hot cores because they are high energy particles and they can make it through the cloud, unlike the photons. So cosmic rays are high energy particles. They're moving at relativistic speeds. They're usually proton nuclei or hydrogen nuclei, they're protons, or electrons, or helium nuclei, alpha particles. 90% are protons in the interstellar medium. So these things come in at relativistic speeds, really high energy. They can hit molecules in the gas phase and drive H2 and H3 plus formation, which drives gas phase chemistry, or they can hit the ice and it's like a cascade of radiation through the ice after they hit. Usually they hit the ice and go straight through, and then they end up causing a string of reactions that look a lot like ultraviolet photolysis chemistry, but it's triggered by this high energy particle hitting the ice and dispensing energy into the ice to cause that chemistry to happen. So Eric Herbst and coworkers actually modeled what happens if an ice undergoes radiolysis. So the idea is in interstellar chemical models, we used to just model the gas, then we added the surface chemistry, then we realized the bulk ice can react too. And so what happens if one of these cosmic rays hits the ice, and this is actually tracking the damage that it does through a computational model, and it can go pretty far in to amorphous solid water ice and cause quite a lot of bulk ice chemistry in addition to surface chemistry. So chemical models, which you'll hear more about later in the week, are very reliant on the complexity of the physical model and the chemical model. And we have simple physical models with big chemical networks, and we have simple chemical models with complicated physical networks, and it's very hard for both of them to be complicated. But we're making major progress in this area in astrochemistry. Yeah?
The scales or dimensions are, it's hard to read. It's,
10 to the minus 6 centimeters.
That's the order of a, that's the order of like 100 angstrom, 10 nanometers
Right.
up to 100
Right.
nanometers.
So most of the ice in the interstellar medium is just a few monolayers of water ice thick. So on the order of angstroms is appropriate.
And order of angstroms.
Mhm.
That's the complex scale. I mean, if you have layers.
So it burrows into some degree on the level of atomic or molecular scale. So it'll go in a couple of monolayers, but it doesn't, sometimes the cosmic rays go all the way through. But so, as I mentioned, there are groups that study the ice and study the chemistry on the ice. This is from Martin McCustra's group, where they put down a water ice and then they added different atoms and molecules to it and watched the surface diffusion and desorption off of the ice, and they can actually calculate binding energies for the ice based on this. Which is really, really important for the astrochemical models, because otherwise we just kind of have to guess as to what the binding energy is. So there are groups doing very active research and trying to measure this under both pure water ice conditions and mixed ices that are more realistic for what we see in the interstellar medium. So once the molecule desorbs, or the atom desorbs, it's in the gas phase, and it's again limited by collision timescales unless something else happens to speed it up. This is a chart that one of my grad students made of the different types of reactions that can happen in the interstellar medium. It's probably really hard to read in this room, I'm sorry. You can have cosmic ray-induced photoionization, cosmic ray-induced photodissociation, elimination and condensation reactions, protonation reactions, charge transfer, dissociative charge transfer, dissociative recombination, when an ion finds an electron and they recombine and then spit out new products, radiative association, where it actually gives off a photon when they recombine, and then neutron. Yeah, I could just keep going. It'll be fine. No, I have to be good. He's like quoting famous people in his talk. So for gas phase chemistry to go, yeah.
Hopefully your other question here. In the dust particles which have been collected, has there been, how much do we know about the morphology? Have there been imaging of these?
So the interplanetary dust particles look an awful lot like soot, actually.
SEM images, for instance?
Yeah, or SEM mostly.
Or SEM.
Yeah.
Yeah, because that matters.
Yes, absolutely. So, to get chemistry to go in the interstellar medium and the gas phase, you have to have an attractive force. Otherwise, we're at the mercy of that collisional timescale that we looked at earlier, which I calculated. My boxes aren't popping up when they're supposed to. So interstellar chemistry is slow, like 159 weeks between collisions before anything happens, and many, many, many kilometers of distance between things happening. So you have to have a process in the gas phase to drive the reactions at a faster rate than what collisions would tell you would be the dominant factor. And luckily that does happen. So, ion molecule reactions dominate. As I said, you have this collisional cross-section limit, the hard sphere limit for two neutral molecules, just based on the size and the speed. If there's an attractive force, you can actually change that rate constant. And what happens here is if there's an anion or a cation near a molecule that can be polarized, they will interact. There will be an attractive force, and this influences the rate constant for the reaction and therefore speeds up the chemistry. So, the effective cross-section is bigger for an ion molecule reaction than it is for just a collisionally dictated reaction. So the rate constant that gives us this information is called the Langevin rate. This is the expression for the rate term. It depends on the reduced mass between the two particles, the polarizability of one of the particles, and the charge on the other one. So in the gas phase in the interstellar medium, ions drive the chemistry because they have the charge that attracts polarizable molecules and speeds up the chemistry beyond the collisional rate. We used to think they were mostly protonated species, but Mike showed that anions are actually there. And so now there's a whole branch of astrochemistry looking at anion reactions as well. And so a lot of the work in gas phase astrochemistry has been looking at these ion molecule reactions and trying to understand their rates. So this is going to be online. I'm not going to ask you to read this here, but this is all the different types of interstellar chemistry that can happen and the basic structure of their rate equations so that you can look at the different reaction rates and get an idea of what actually influences the chemistry. So if we put it all together, I'm going to walk you through what we think happens. This is always under constant revision. As I said, astrochemical models either assume a big chemical network and fairly simple physics, or a simple chemical network and more complicated physics, and we're working hard on putting the two together, but that's a very challenging computational problem. When I was a grad student, Steve Charnley had the probably most elaborate complex organic chemistry models of the interstellar medium. Steve had done a conference proceeding on this work, and he went through and circled the things he thought were detectable and sent it to my thesis advisor, and that was the basis of my thesis project. It turns out nothing that Steve circled have I yet actually either made in the lab or detected in space. But it was a great start to a fun thesis project. So the idea here is we have hydrogen atoms, oxygen atoms, carbon atoms, nitrogen atoms on an interstellar dust grain. We have a lot of water ice, things can diffuse. You can build up CO from carbon and oxygen and then to CO2. If you add hydrogen to the system, you start to make radicals. If they keep sequentially adding, you can get all the way to methanol or methane diol, and then you can keep adding other atoms and branching out in the complexity of the chemistry by doing one atom at a time onto these species. A lot of these molecules have been detected in ices. A lot of them haven't because there aren't available laboratory spectra to be able to do that work. I've been after methane diol and aminomethanol since I was a second-year graduate student. Aminoethanol is this one. It is stable. You can buy it in a bottle, and that was the first thing I did in graduate school, and I still haven't found it in space. But aminomethanol is the precursor to glycine in space. Methane diol is the precursor to sugars. So for astrobiology, these two are really important, and my group is actually trying different chemistry now to try to make them in the lab. Things can exist for a long time in space that are really, really hard to make in the lab. And there are lots of people in this room who've built their careers on trying to make unstable things, Mike and Daniel in particular. So, and Lucy, when she gets here, Lucy looks at metal-containing species. A lot of times they're ions or reactive species. So if this is what's going on in the ice based on just atoms moving and assuming everything's locked in at 10 Kelvin, you get some complexity but not a lot. And then the assumption was the star forms, things warm up, they get kicked into the gas phase. You have a lot of methanol because that's that very first branch on that tree of ice chemistry, right? Here's methanol. There's actually a beautiful laboratory study from Naoki Watanami's group where you can start with CO ice, add hydrogens, and actually watch it sequentially go all the way to methanol. So we know that that happens in an ice. So the star forms, things warm up, they go into the gas phase in this hot core. There's a lot of hydrogen in space, which means there's a lot of H3+ in space. H3+ likes to give its proton to everything it meets. And so usually if there's a gas phase molecule in the interstellar medium, it has its corresponding protonated version at very high abundance. This is a really nasty spectroscopic problem that no one has ever cracked, and this is my life goal, is to actually get the spectrum of the species so we can go and look for it in space. But the assumption that Steve made in these models is protonated methanol forms, and it goes around and reacts with all the other highly abundant organic molecules that could be forming on the grains, and then those go on to make even bigger molecules. So if you're going to build up complexity in the interstellar medium, the assumption up to about 20 years ago was that it had to be gas phase ion molecule chemistry to do that, because those Langevin rates were what drove that type of chemistry. There's some problems with this assumption, and this was basically the basis of my thesis project. Around this time in the early 2000s, there were lots of groups working on this, and Horn and Eric Hertz's groups showed that, so methyl formate is kind of the signpost of complex organic chemistry in a star-forming region, highly abundant in just about every star-forming source. The assumption in the previous models was it only forms in the gas phase from ion molecule. Eric and Ann Horn actually went and ran calculations on all those ion molecule reactions, and none of them were efficient enough to make it at the level that we need to explain observations. You go back to the grain surface chemistry, at 10 Kelvin, there's no way. But if you take a look at methyl formate and its structural isomers, acetic acid and glycolaldehyde, if they're forming from those single atom addition reactions and it's indiscriminate, it adds to whatever bond it encounters, you would think they'd be fairly similar in abundance. And it turns out methyl formate, despite being not the most thermodynamically stable of these species, is actually very much more abundant in Sagittarius than acetic acid and glycolaldehyde. Glycolaldehyde is incredibly hard to detect. It's the simplest sugar-related species in space. Acetic acid is actually the most thermodynamically stable, but it's highly reactive in the ice because it's an acid. I was the first person to come along with these meetings and start saying the word esterification, which I think scared my astronomy colleagues. So if you have an acid and an aldehyde, you can actually have them undergo a very energetically favored reaction to form a bigger molecule from that, and we think that might be what's giving up all the acetic acid. Around the same time, groups started to look at low mass star forming regions, so stars that are about the size of our sun. This is hard to do observationally, and the interferometers have to get good enough in radio astronomy to be able to match the beam to the source size and see things. But they started seeing methylformate in low mass hot cores and shocked regions and places where there was no significant gas phase processing going on. So the assumption was we'd missed something, that methylformate must be forming on the ice surface somehow, and there was some chemical process that needed to be added. I'm a chemist. I looked at these molecules and saw functional groups. And so I actually worked with Rob Garrett and Eric Herbst. I never worked for Eric. I just did this in my supposed free time. We sat down and added thousands of reactions to the models, looking at these functional groups and looking at their radical counterparts and how they might react in interstellar ices. And we added all of these reactions to the models. So the assumption is if you have a cosmic ray or a UV photon, it comes in, it hits the ice, and it can break apart these simple ice species to make these radical species. At about 15 or 20 Kelvin, all of these are mobile on the ice surface, and they can find each other and react through the Langmuir-Hinchelwood mechanism. And so you can actually build up a very, very complicated network of chemistry. Oh, I have a little movie. There they go. They find each other, they react. And so you can directly, in one step, get to methylformate and glycolaldehyde. It takes 2 steps, and you can get to acetic acid. So the thinking was we had missed a whole suite of ice chemistry in these models. And so I actually, while I was a postdoc, worked with Eric and Rob to go back and add all of this chemistry into the models and update the ice.
Susanna?
Yeah?
I know that it will take from your time, but perhaps you could say a few things about how this network is built out.
I think Stefano's going to do that later in the week.
Yeah,
We decided to
but then-
split the topics that way.
But maybe you can say a few words.
Yeah, so the kinetic models are basically assuming everything's governed by rate equations. So you write out a list of reactions and their rate equations, and then you do a point-by-point calculation solving the differential equation for the time rate of change for each species and each physical condition along the trajectory of the model that you want to run. So they're computationally intensive. The physical models Eric uses are usually pretty simple, so we can put thousands and thousands and thousands of reactions in. Sometimes they flip that and they pull out the most important reactions and then do a really complicated physical model. Depends on the study. But for the most part, it's writing out reaction rates and then putting them in a model and running calculations based on the kinetics. So the physical model we had to do to get this to work was to assume that the star gradually warms up. And all previous hot core models, they would let it run at 10 Kelvin, and then they would crank it up to 200 or 300 Kelvin and then let it run. This is not how star formation works. You don't flip a switch and suddenly have everything at 300 Kelvin. And Rob had actually worked with Serena Beatty in his PhD project to look at proper models for this temperature warm-up of star formation. So we put this warm-up in, it's a gradual increase, and so now the chemistry on the ice had time to actually form new species because we didn't just eject everything into the gas phase. So we redid the models using this physical model and my chemistry, and I've color-coded it here for you so that you can see here are these radicals that form. Here are the radical reactions that can happen when the ice is warmer than 10 Kelvin, but still not completely warmed up. And all of these species are readily seen in multiple star-forming regions in the interstellar medium. So for the first time, we had a surface reaction network that could actually start to predict molecules that we could see in the interstellar medium. There's a lot of work to be done. We don't get the ratios right in most sources, but the chemistry is feasible, which is really exciting. There's a lot of debate in the field right now as to whether solving with reaction rate equations is the way to do these models. So like Herma Kupin is trying to do models where it's a Monte Carlo approach, where she follows specific species on the ice and does a full Monte Carlo simulation. That is even more computationally expensive than what we've done here, so it's very challenging with big networks, but there's a lot of progress being made.
Susanna, can I
Yeah.
ask you a quick question?
Sure.
So do we know how much these big guys can diffuse on the surface of grains? Because
So-
hydrogenation is a simple process that we know can occur. We also see this in the
Right, Martin McCuster's measured some of them and looked at diffusion rates and binding energies, but not all of them. So there's still open work to be done in the field to try to get that information. We calculated based on the dipole moment what the binding to the surface should be based on that Collings et al. Paper that Martin published where they had done a bunch of simple species and we just tried to extrapolate up. But yeah, if you are looking for inspiration for laboratory projects, there are a lot of things in astrochemistry that we simply have to assume or calculate to the best of our ability that all need to actually have laboratory measurements to back up the assumptions. So binding energies and diffusion rates are a big chunk.
Because my feeling is that these heavy guys cannot move.
They don't move too much, no, but the radicals that form them do, and those are the things that are new in this model. We have now gone well beyond what inspired these models, and people are now seeing complex organic molecules in prestellar cores where the star hasn't lit up yet, so it's still at 10 Kelvin, but it's gravitationally collapsed into a clump. And you can see things like methylformate now in a prestellar core, which means there are cold, less than 10 Kelvin chemical reactions that are happening in these sources that have not yet been included in all of the models. So we have even more work to do. Every time we get a better telescope, we find out all the things we didn't know with the previous generation. Anton Vasyunin has been working on a model looking at reactive desorption reactions in these cold clouds where the idea is a reaction happens and it's hot enough, it gives off enough energy that it can actually eject the products into the gas phase. So you could have chemistry happening in a 10 Kelvin ice where the energetics are such that it can actually kick the product into the gas phase, even though you don't have any star formation yet to cause the gas phase species. So this is a whole new area of study in astrochemistry. People are trying to go and measure these reactions and see what's important in interstellar chemistry. The better the telescopes get, the deeper we can go in terms of signal to noise, and so the more and more and more complex molecules we find in these star-forming regions and prestellar cores. How am I doing on time? Good? Okay. I was conservative on my slide number because I thought I would give more questions. Does anybody have any questions? We have about 5 minutes left. Yeah?
You kind of, I guess, touched on it right there. These larger molecules, like you asked earlier, where they don't have very high mobility,
Right.
Are these things sticking around on the ice mostly, or are they being
Yeah,
picked off
yeah.
at a higher rate? And being
If you
stuck
use
around?
the binding energies and the diffusion rates that have been measured for some of the more complex species, you actually see that most of it comes off when the water ice evaporates because it's bound in water ice.
Yeah.
So that's 150 Kelvin or
So obviously you'll see some of these towards the
Yeah.
star-forming region
Yeah.
where your temperatures start
Yeah.
to increase.
I should mention a definition that'll be useful to have later on in the week. So in interstellar chemistry, the definition is a complex organic molecule has more than 5 atoms. So methanol is complex, formaldehyde is not. So that is a very handy definition to have. And now there's this ICOM thing. the interstellar comms, and I don't know, they keep adding to the definition. But if I say a complex organic molecule or a COM, I mean more than 5 atoms. Methanol or bigger, basically.
What's the limit on the size of a molecule that can actually desorb from this heat reaction?
I don't know that number. I think it depends on how polar it is and what the energetics is to break the bond to the ice versus the energy that's released from the reaction. So if it's a really exothermic reaction, I would assume it can overcome it. Things to think about. So we do gas phase oxygen, excited oxygen atom reactions with organic molecules, and Karl-Oberg's group has done that in the ice. And so that would be a case where it's so exothermic, I would think that this reactive desorption would be really important. Yeah.
So you mentioned there are many coordinated species of complex molecules.
Yes.
And you also mentioned that ion molecule collisions are probably faster.
Yes.
So can you comment a little bit how fast is the rate of those ion molecule collisions?
Several orders of magnitude faster than the collisional rate.
How about compared to the surface reactions?
That's a hard comparison to make because the surface depends on the physical environment. So if you're looking at surface reactions, it's a dense cloud or a prestellar core. If you're looking at gas phase reactions, it's a hot core or a hot carino. So it's hard to compare because they're in 2 different physical regimes. And so we can't really have much of both types of chemistry happening. There's certainly a transition region where they could both happen. But for the most part, we separate the ice diffusion from the gas phase. There is some exchange, 50 Kelvin, 100 Kelvin, something like that, but for the most part, if you're looking at a hot core, you've assumed it's all evaporated. Yeah?
How does grain charge play into the surface reactions and also the structure of them?
We don't know. You just found a proposal for your PhD project. Yeah, there's a lot that we don't know. We don't know how grain charge and magnetic fields influence the chemistry either. There are all sorts of things that could have played a factor in that, and there's not a lot of work being done. It's very hard. The techniques that you use to study ices, you need to be able to reflect the infrared radiation. Like it comes through the ice and then reflects off the stage and goes to the detector, so you can do spectroscopy. So it's really hard to do those experiments with a surface other than a metal. But there are groups that are looking at ice surface analogs and then trying to understand the chemistry there. And then understanding the bulk ice and what happens if the cosmic ray makes it through to the grain and what can happen at that interface is also an area that's relatively unexplored. All right, mic's up. Mike's like, please don't make me. All right, I'll be around all week so you can ask me questions. Yeah, sure.
How much is known about the dipole moments of these molecules?
You can actually get really reliable dipole moments from electronic structure calculations. It's the one thing that we know we can almost always get good enough for our purposes for observations.
But how large are they?
What's that?
How large are they?
Depends on the molecule and its symmetry. I'll talk a little bit more about that tomorrow night. I think I've been delegated as the rotational spectroscopy person for this week. So, so yeah, it all comes down to the structure of the molecule and what the electric dipole moment turns out to
That
be.
affects collisions.
What's that?
That affects collisions.
Yes,
How
yes.
the molecules and the molecules and
Right.
molecules collide and the surface. Okay, any more questions for Susanna?
We've got one.
Yeah, one more.
One more, yes.
Maybe this will get answered later, but how computationally intensive are the grain simulations? I imagine if those were not as bad, then you could.
I'd say the most computationally challenging are probably Herman Koopman's monocardinal models. Rob Garrett has kind of ventured away from reaction rate models and is looking at other ways to do that calculation. Tom Miller and Eric Herbst are still mostly doing reaction rates. And then there are increasingly complicated physical models, like Catherine Walsh was trying to take my network and put it in a disk model. And right now there's no turbulence, but we know it needs to be there. So yeah, it depends on, Yuri Aikawa is looking at hydrodynamic models, but with a really simple chemical network. Yeah, it's varied depending on the problem. Eric and Valentin Wakeholm ran a really interesting study where they ran the full grid of chemistry in the full model and then looked at, like they reran it with different limits on certain key reaction rates and looked at which reactions actually had an influence, and they could boil it down to a set of 20 or 30 reactions that were actually the most important chemistry in the model, and then everything else is icing on the cake, I guess. But yeah, there's a lot to be done in the modeling category. I only have 2 W's, you have 6.
Until tomorrow.
Hey, careful, you're breaking your body. That's not me. Just say it's like a wall to it. It's not good. How far to the nearest hospital, by the way? I'm asking just in case I get bitten by something.
That's the only hospital that I actually consider a hospital with mass general. Let's go 25.
How many hospitals in New York?
If I get sick, take me on a helicopter or a private jet to MGH.
Yeah.
There's MGH and then
There's MGH and then there's about under the dirt, there's an hospital.
We'll take it outside.
Okay, so the first lecture by Mike McCarthy, who is now what is known as Harvard and Smithsonian, was still considered Harvard. Will give his first lecture, which is sort of a historical overview of molecular astrophysics.
Yes. Thank you, Lucy. So it's a great pleasure to be here. It's good to be out of Boston. And so I thought I would change gears a little bit from the first 2 talks, hopefully give a compliment. But I wanted to start off with a little bit of history, as I call it, the 6 W's, what, when, where, why, how. So you see it's already going off the rails because it's only 5 W's. And so, like Susanna, my background is actually in chemistry. I've never taken a course in astronomy, so I can't answer any questions about where the galactic center is or where Jupiter is or anything like that at all. You'll have to ask somebody else. But what I do want to emphasize is that, and that John mentioned this as well, much of this astronomy is remote sensing, right? We can only interpret the universe from emitted or absorbed or scattered radiation. And much of what we can see, or much of what exists, we cannot see directly, or very difficultly. Hydrogen itself, molecular hydrogen, only has very weak quantum transmission to the infrared. So we have to infer the existence of hydrogen from other molecules like CO. And there are many other examples. Benzene, for example, you can't observe from the ground from an infrared facility because it's absorbed by the terrestrial atmosphere. And so this then becomes an issue to a large extent in taking the spectroscopic information, these emission and absorption that we observe,